All right, so welcome back to CME 194. Today we're going to do a little bit different thing. We got Rob Schreiber from HP Labs who's going to talk about performance in NPM.
So let me just briefly tell you that I've been doing parallel computing since 1977, which is the year I got my PhD. It seemed like it might be a good thing. It was a new thing, so it was a bit of a chance. Well, it's worked out well. As you know, everything that's a parallel computer, everything, my phone is a parallel computer, everything's a parallel computer, and to do serious computational science today, you don't have to do parallel computations, but most of the time that's what it's all about. I'm at HP Labs now. I've done parallel computing at NASA, at startup companies, and here, where I was an assistant professor long ago. Why are we doing MPI? Why are we worrying about writing parallel MPI programs?
Solve big problems. Because our computers aren't getting faster quickly enough.
So speed and problem size. Anybody have a different? Those are my answers. Anybody have a different?
Memory.
Yeah. So problem size as in disks are too ridiculously slow to be useful for anything really, except for archiving data. So we presume that the memory, the size of the problem must not exceed the amount of memory available on the machine. Now, why not just buy a small machine and load it up with more and 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 more memory?
I cannot address it all.
It cannot address it?
I mean, like
That's right. There's a limited number of address bits in a given architecture. 40-something typically now, yeah.
Well, I mean, with 64-bit address space, I think that will be less of a problem. But
Someday, maybe.
Yeah, someday.
Yeah.
Perhaps. But
Yeah.
I think the bigger problem is that you're not going to be able to co-locate all that memory close enough to the CPU that it'll be useful for you.
Yeah, how many DIMMs would it take to build a petabyte of main memory? And it would be a very big, it would be a very funny looking PC. Furthermore, at today's prices, a petabyte of memory costs $10 a gigabyte. So a petabyte is 1 million gigabytes. So you'd spend $10 million for the memory and $200 for the CPU.
Sounds awesome.
You think you might improve the overall cost effectiveness by spending like maybe $600 for 3 CPUs, maybe, right? So it's just a kind of sanity that you would scale up the compute power along with the memory and the problem size, yeah. And of course, one of the advantages of a cluster is that you buy these processors and memory in packages that have a reasonable ratio of memory to processor, and then you start making copies. You get memory proportional to processors. You also get something else that's vitally important that grows naturally, grows in a linear manner as you buy 1,000 machines. You can't process unless you can get at the data. The key limit to computing on a sequential machine now is this von Neumann bottleneck it's referred to. The fact that the memory is slower than the processor, right? When you do a floating point multiply, you take 2 floating point operands and you create a result. So that's a total of 24 bytes. How many bytes of memory, how many bytes of information can the memory provide to the CPU per floating point operation? If you pedal to the metal, max out the memory bandwidth on a machine like yours. Anybody got an idea?
Hundreds of megabytes per second. That we need.
Maybe even up to a gigabyte per second. But how many flops per second in a modern 4-core machine? It's like 4 times 3 gigahertz times, there's the SIMD unit, the little vector unit in the processor. My workstation at work does 50 gigaflops on matrix multiply. It's a nice big clunky machine, but it's a few years old. 50 gigaflops, 50 billion operations. If you needed to fetch all of the data from memory, you'd have to have 24 times 50 billion. That's like a terabyte per second of bandwidth. So, and you've only got a gigabyte per second of bandwidth. You're off by a factor of 1,000. So the only reason that there's any sanity in the world is the cache hierarchy keeps the frequently used data close to the processor, so that only rarely does the processor need to actually go to the memory to get anything. But this memory bandwidth is still a critical resource, and when we replicate machines, as in a big cluster, we're buying processors and memory capacity and memory bandwidth all in a sort of sensible, balanced way. All right. So you've pretty much covered the reasons here, and I think the dominant reason for MPI is big clusters, and the dominant reason for big clusters is to scale the machine so it's big enough to hold big problems. Why are problems getting bigger? Does anybody have a good idea about that? Big. Why big?
Because they can.
Because they can. Oh, you're right.
Will not make it bigger.
You're absolutely right. Well, I mean, but there, of course, is a payoff in general. I mean,
Yeah, you can be more accurate.
resolution. Yeah. So to get, we are interested in accuracy in science, in reducing error bars. So we naturally fill up the whole machine in order to improve the resolution of the model. Finer meshes, more grid points. That's one good reason. Eh? Anybody else? There are new compelling reasons to do more in memory, in addition to either more particles or bigger molecules, or a finer mesh. Multiphysics. So you're modeling multiple phenomena, and they communicate every time step. They have to exchange information, say. That's the kind of thing you have in mind.
Yeah.
So you got to do them simultaneously. Right. And there was a kind of bad old idea, which is that I'll use a machine in New Jersey to do one part and a machine in Connecticut to do another part, and they'll communicate over the grid, but bandwidths are pathetically bad and unreliable. So you really need it all in the same machine. How about anybody looking at uncertainty quantification? So uncertainty quantification is all about, putting an error bar on the computational result. The sources of error are many. The most obvious is I'm not really sure what the problem was. I measured the input data. I have a probability density for the parameters of this problem. I'd like to know the corresponding probability density for the output. And the dumb brute force way to do that, but it's commonly used, is sample from the input, generate samples of the output. So we're solving this problem not once, we're solving it again and again and again. Now you could do that sequentially, one after another, but then you might have a long wait. So if I can stick all of those or a bunch of those problems on the same machine at the same time, so much the better. So we need more memory as much as we need more performance. Okay, now I'm going to introduce the oldest performance idea known to man in parallel computing that you've probably seen before. Given the shape of the room, I think more of you will see better over there, which is speed up. And you probably have seen this. Anybody here never heard of the speed up function as a function of the number of processors employed? It's okay. It's all right to not know this. Well, I'll do it anyway because I don't believe you. So if I'm solving one problem on a parallel machine and I use P processors, the speed up is defined to be the time. I want speed up to be bigger than 1. So I guess it's the time on 1, if P equals 1, divided by the time if I use P processors. That's how much my parallelism sped up by what ratio it sped things up. If I use 2 processors, it takes half the time. I got a speed up of 2. So if the speed up on P is P, that's perfect speed up. Never happens. If the speed up on P is like 0.75 P, if it grows linearly with P, that would be linear speed up. The common case in parallel computing, if you fix the problem, and its size. I'm inverting a million by million matrix. Here's speed up equals P, that's ideal. Here's linear. And here's ugly reality. Okay. Sublinear speed up. Now, it is sometimes observed that reality does something funny like this, so that over here towards the left end of the picture, the speed up dp is greater than 1 for a little while. Superlinear speed up. Does anyone have a theory about how that could happen? I tipped my hand earlier. It's a memory bandwidth related issue.
Improved caching.
Improved caching, yeah. What's improved is that you have more cache.
Yeah.
So what happens is, it may not be a smooth curve. In fact, these curves are never smooth. This is a cartoon. At some point, you suddenly discover there's enough cache that the whole problem now fits in cache, and I never have to go to main memory. So that gives you a jump in performance suddenly when you finally bought enough machines that the problem fits in cache. Of course, that means you're solving too small a problem. Why'd you buy all those machines? You know, you really want to solve a bigger problem. So that's just a kind of not interesting. This tail is the interesting thing. We'll get a little bit about that. And efficiency is sometimes defined as speed up over P, or more properly, processor efficiency. But it's a dumb idea because efficiency is an economic notion, and this thing, the denominator, presupposes that the only thing I was paying for was the processors, whereas in fact I paid for my time in writing the damn program and all the memory and everything else. So it's in some ways a dubious idea. So that's parallel computing 101.
I have a quick question.
Yeah.
So, I mean, when you asked the question, why are we doing parallel computing?
Yeah.
No one actually said, like, to do it faster.
Yeah.
You just want to do bigger problems.
Yeah.
So wouldn't, like, a more proper definition be to say, if I have a problem that's double the size and I give it double the amount of processors, it took the same amount of time?
Yeah, there's a problem with that, though, that I'll give you right now, just for the fun of it. Suppose I'm solving a typical problem in computational science. du dt equals f of u. U equals a function of x, y, z, and t. That's four-dimensional space-time. And most of the methods we know involve putting down a mesh that discretizes x, y, z, and t, and then starts from some initial condition, u of x, y, z, t equals 0 is some known function g. So we start with g, and then we march forward in time one step at a time. To go to step n requires knowledge of the solution at step n minus 1, and often we keep around a few of its brothers just to get more accuracy. Well, we can typically use as many processors as we have mesh points in the x, y, and z direction. The work across space is parallel, but the work going forward in time is sequential. So the irony is that the bigger the machine and the bigger the problem I have, I grow the machine so that it makes the number of mesh points, spatial mesh points per processor, a constant as I grow things. But the number of time steps to get me, oh, I have to make the time steps smaller and smaller as I do that because of numerical stability, the so-called Courant-Friedrichs-Levy condition that says that you better propagate information as fast in the numerical scheme as it propagates in the physical world, otherwise it can't work. So you wind up taking more and more and more time steps sequentially to get to the goal of covering a certain amount of simulated time. And this is a problem we face today on very big machines with very big problems, that sequential nature of the time step. Yeah, people are working on ways to parallelize in time. Okay. So, did that get at the issue you just raised about?
Yeah, I think it covered some of it. I
Yeah.
guess.
And another view is, of course, if you solved a given problem and it took you an hour, what's more interesting to do next year? Solve a much bigger problem in an hour or solve the same problem in 1 minute? I mean, who cares about... I guess if you needed to solve a bazillion little problems, yeah, I'm not sure why. To me, the compelling issue is to do a more interesting scientific simulation by increasing its accuracy rather than just doing it faster. I suppose in some cases where you might have an economic setting, it might be that there's an economic payoff to doing things faster. But speeding up a given problem, let's talk about this speed up a given problem. You're going to hit that phenomenon about speed up. So there'll be strong limits to how much faster the solution to any given problem can be made by parallelism. All right. So let's talk about what some of those limits are. So the first is Amdahl's law. It's conventional to treat this first, even though I think it's the least interesting, least important thing. So anybody hear of Amdahl's law? Good. Tell me what Amdahl's law is.
Basically, it tells you how much your program can speed up.
How much you can, based on?
Based on what portion of it is sequential in nature.
Right.
What
Okay.
portion can be parallel.
Exactly. So suppose 1/10 of my program's work must be done sequentially by one processor. What's the maximum? But I have infinitely many processors. How much speed up could I get? This is easy. Yeah, 10x. Originally it took you 10 units of time. For 9 of those units, use infinitely many processors, and they're done in no time. But that remaining 1/10 still requires one processor, takes the same amount of time. So 1 over the serial fraction is a limit, an upper bound on the speed up. That's called Amdahl's law, even though it's not like Moore's law, because Moore's law is just an observation of an empirical phenomenon. You can't prove it, whereas I just proved Amdahl's law, more or less. I call it Amdahl's theorem. And by the way, Amdahl didn't prove it. He gave a talk at a computer conference like in the 1950s, at which point people were just beginning to think about parallel computing. And he was working for IBM and was part of the old guard, and I think didn't like the idea, so he said, 1/3 of typical programs must be done sequentially, so you could never get more than a factor of 3. We're building today machines that are going to have 1 billion operations happening in parallel. So either we're crazy or we know Amdahl wasn't wrong because it's a theorem, not a law. So what can we conclude if it's sensible to have something that does 1 billion computations at once?
Certain problems are almost all parallelizable.
Yeah, it's if you stay away from stupid stuff like, can you parallelize Microsoft Word? No is the answer. and solve big scientific problems and pay attention to the issue of parallelism, design parallel algorithms and data structures, you can drive that Amdahl fraction down to a vanishingly small amount. And that's been the typical, that's happened widely enough that this is now the mainstream in computational science. So Amdahl was right but irrelevant. But there are a lot of other ways to get crappy speed up. So let's talk about what those are. What else? In MPI, you distribute the work and you distribute the data, right? Oh, way number one is don't do that. Rely on some piece of software to do it for you. Forget it. That won't work. You do it yourself. And what comes first, the distribution of work or the distribution of data in an MPI program, typically? I know you're just beginners, but what have you seen so far?
You distribute the data first.
Typically, the data distribution then determines the work distribution. All right. Suppose I'm parallelizing an off-the-shelf program, and it does some computations on large meshes, and it does some computation on large matrices. So clearly, I want to distribute those. But it also has scalars. What should I do with those?
Spread them promiscuously.
Yeah. They should be, or in some, well, that would mean randomly scatter them around the machine. That would be a pessimal distribution. Because if I then needed to add scalar A to scalar B, one of them would have to move to where the other one was, or they'd both have to move to an agreeable neutral location.
I guess ubiquitous would be a better.
Ubiquitous rather than promiscuous. I love it. Exactly. You should replicate all scalars. You should replicate all sequential computation. It's still sequential. The sequential computation is still, the Amdahl theorem is still valid because you're doing the sequential work, you're doing it redundantly. You can't claim credit for that. Some people do. But at least everyone would immediately have the result of that sequential computation. I wouldn't then need to broadcast the result. So a dumb mistake is to say, oh, we'll make rank 0 special, and everything that has to be done by one thing, we'll just do it on rank 0. No, because then how does rank 1 find out? Just have all that sequential and scalar stuff done in a replicated way. So I call that sort of under-distribution. There should be nothing done sequentially if you can avoid it. And of course, when you distribute the load, if you distributed the load in a matrix addition, what would be a reasonable way to distribute the load by distributing the data?
Tiles. In tiles.
Tiles of some kind, and equally sized. Right. So you can easily, in that case, with a well-structured thing like a matrix addition, you can make sure everybody has the same load. Right. But now it's a sparse matrix. Now it gets a little more interesting. Okay. When the amount of work associated with a given piece of data may vary. So now the load distribution becomes a source of inefficiency potentially. Let's do an example of, all right, I'm going to do a non-trivial example here. I'm going to talk about matrix factorization by Gaussian elimination, by LU decomposition, right? the standard way to solve a system of linear equations. And I'm going to think about that in a world in which I've taken the columns of the matrix and I've distributed the columns among the processors so that every column is on one processor. Every processor has a subset of the columns more or less the same size as every other processor's subset. A common way to do that is by some kind of cyclic distribution, or as a friend of mine once said, you deal out the columns to the processors. Oops. So the reason for that is that the way you do this decomposition is you take a column 1 and you subtract column 1 from every other column, a multiple of column 1 from every other column, so as to whoa. What? Oh, I guess we need this thing, huh? Maybe not. So you're going to subtract a multiple of column 1 from every other column. You do that so as to eliminate non-zeros. Then, having subtracted column 1 from column 2, you do something to column 2. You divide it by the diagonal element. And then you subtract a multiple of column 2 from all the subsequent processors and so forth. So a typical way to do this would be to write code that subtracts column 1 from all of these. Then, having done that, the processor that owns column 2 figures out that it owns column 2, does what it has to do to column 2, and then broadcasts that to the other processors, which then subtract a multiple of column 2 from all others, and so on. So the way you write that MPI code is something in which the order, the sequence of operations, is something you had in mind and you bake into the code. It knows what messages to expect from where. It does MPI receives for those messages in a predetermined order and carries out the operations on its own data in a predetermined order. Now, I've described this whole process as being one involving two kinds of operations. Let's call them operations A, which is something that's done to column K before it can be subtracted from all others, and B of Kj, which is what happens when you subtract an appropriate multiple of column K from column J. And there's a directed acyclic graph showing the dependencies of all of these operations. It all starts with column 1 being modified by dividing every entry by the diagonal entry. And then there's a whole bunch of B's, B12 through B1n, that depend on that. And then it turns out that A2 depends on B12, and then there's a whole lot of B's that depend on that, and so on. This whole thing expands into a large directed acyclic graph. And your program bakes into itself a particular order or a partial order that determines when things are going to happen. So you know that you're going to do B23 before you do something else, because you receive the message and you do the work in that order. However, the networks in these machines can do funny things to the arrival of messages. They can delay messages. They can have them arrive in different orders. And when messages come in from two different senders, who knows what the order they'll arrive in is. So there's a second style a different style of writing MPI code. Have you seen the MPI any source, whoops, and the MPI any tag options in receive, MPI receive? You know, you can bake in the source or the tag, or you can say, I'll take what I get, and I'll figure out after the message arrives what were the tag and what were the source. Well, another way to write these codes is to write them using this stuff, to say, I'll accept any message. I'll figure out what that message was by looking at the source and the tag, and I'll react. I'll do the work that I can do that becomes enabled by the arrival of that message. So this makes for an asynchronous, less predetermined sequence in which you do the work. Furthermore, you pay some attention to the fact that there are certain actions that have a lot of successors in this graph. And not only that some of those successors might be more important than others because they are the immediate successors of other critical path kinds of actions. So if you ask what is the longest chain through this DAG, that's the so-called critical path, you want to favor things that are on the critical path. You want to send out data from actions on the critical path as soon as you can to enable other things to get going that might turn out to be bottlenecks. So this different way of scheduling the MPI that's more opportunistic and that favors things that are more important, that's a way to, even in a thing that has no sequential fraction, that is perfectly load balanced, this is still a way to get further performance improvements. So all of the software for distributed numerical linear algebra went through several phases, and kind of recent change has been to adopt do things as soon as you can do them, and don't bake in the schedule a priori. It's a completely different style of distributed memory computing that's popular in some circles. Where nothing happens except for that a message arriving triggers it to happen. This reactive style. Okay, I'll give you another example of performance issues related to how you do message passing. There's one of the collectives that you may have seen is MPI all to all. Have you seen that? So you know, if you, in an MPI all to all, every rank has some vector it needs to send to each other rank. And they're all different, right? So everyone's going to send out, if P is the number of ranks, everybody's going to send out P minus 1 things and receive P minus 1 things. Suppose there was no collective. Well, I'd write it myself. I'd write for other rank equals 0, other rank less than or equal to less than P, other rank plus plus. Is C okay? MPI send, buffer, sub other rank, to other rank, etc. I'd send the message that I have to the other guy unless other rank is only if other rank is not equal to me. Right? Don't send to yourself. And corresponding receives. Now I'm smart. I'm not going to use receive for fear of deadlock. So I'd use I receive. For 0 to. So
Aren't you going to deadlock on the send?
yeah, I would probably have to reverse the order and do the I receives before the sends. Yeah, otherwise I would definitely deadlock on the sends. So consider that the order is reversed. So this does it. Now improve it for me, please, from a performance point of view. Everyone's going to hit their send to 0 before they hit any other send. Now the I receives will all have been posted. So over there on rank 0, you'll have lots of message sort of, you know, they're like welcome messages waiting. I'm waiting for a message from 1, from 2, from 3. So nothing's going to deadlock, but what's going to happen?
So everyone's going to have to wait. Well, everyone's going to be sending to 0, and 0 is just going to have to take all those messages one at a time.
Yep. Because one thing you don't have is a parallel port into the network. You've got a little soda straw into the network over which the data are flowing. So one of those sends is going to get to 0 first and arrive, and it'll take time. And they'll sequentialize. And nobody's going to get to his second send, because they're blocking, before his first send is finished. So we've already improved this. We've improved this twice, I believe. First we would, well, what I should first of all certainly do is I send so that you can post those sends without waiting. But that really doesn't solve the problem, because the sends to 0 are going to, you'll now have told your MPI library about all the sends that it has to do, but it hasn't done them yet because you've used iSend. And it's going to probably try and do them in the order you specified. It might. You have no control over that.
So try sending, starting at each processor, sending to the processor with rank 1 higher, and kind of cycle and receive from it.
It's a way better idea. It might be a good idea to post all the receives first, just on general principles, but then start sending in such a way that you send to him, he sends to him, he sends to him, all around, so that all of those things could actually happen in parallel. Modulo maybe network traffic considerations that we can't really think about, but at least we know only one message would be coming into him. And then next you would send to the guy equal to u plus 2. Of course, treating it all as a circle of processes. Yeah. So that's a much better idea. That's a scheduling idea, avoiding hotspots in the sort of send-receive graph. Yep. So let's see. So the new improved version is do I sends, do I receives. I don't think it matters, but I would try both, seeing which order is better. And of course, it would no longer be for other rank equals 0, but rather other rank equals me plus 1. And I don't really want to do that as a while loop. So, yes, so I'd say other rank equals me plus 1, and I equals 0, and then while I is less than p, I plus plus, it might be less than p minus 1. Let's see, here's how we do this. Other rank equals 1, other rank, you get the idea. You send to the guy to your right, and then the guy to the right of him, and so on, so that it all goes around the circle and no messages collide. I think there are other ways to improve this, but I'm not quite sure what they are at this point. So a good reason to use the collectives, of course, is that you're now leveraging tons of research that's been done over the years on all manner of improvements that go well beyond these simple ones to get the best possible performance. But that may not always do it for you, and sometimes you've got to use send and receive. So here's another example. And you probably know the right thing to do, but let's analyze what happens if you do the wrong thing. Think of the ranks as a straight line, a row, and the application requires that every rank send some big message to the one to its right, the one whose rank is one more than yours. So the last guy has nothing to send. The first guy has nothing to receive. Everybody sends to the guy on his right, if he has a guy on his right, not circular.
Oh.
Not circular, straight line. All right?
If you're just doing modulo, then it would be automatically cyclic. That's why.
It would be what?
It would automatically be cyclic if you did it with the modulo option.
Don't use mod. Just say me plus 1.
Yeah.
If me less than numprox minus 1, then send to me plus 1. If me greater than 0, then receive from me minus 1. All right? So. All right, I use pseudo MPI. I can't stand writing MPI com world, so. Is this going to deadlock? I use send and receive. I didn't use iSend, so it might deadlock. But think about it a little farther. What's the highest numbered rank going to do? For him, me is equal to numprox minus 1. So he'll skip that, and he'll go straight to the receive. So the send on the processor to his left will see that, and that send will be enabled because the corresponding receive has occurred. So let's I'm tired of talking in abstractions. Let's say there are 8 ranks numbered from 0 to 7. So 7 will fall through here and post the receive. 6's send will meet 7's receive, and then that will happen. So 6 will be able to do that. And then 6 will, after having sent, after the data have all left and send receives, 6 will reach the receive statement. So 6's receive will then enable 5's send to go. And it'll all work. You won't see a deadlock. Your program will work. It'll just work really, really, really slowly because something that should have happened in parallel is happening sequentially. You've induced a dependence here by the clunky way you used send and receive. All right, so in case Ryan hasn't already told you this, it probably has. Real MPI programmers never use blocking send and receive, not that I know. Everybody always uses I send and I receive, which means you have to deal with putting in the weights in the appropriate places, but the payoff is well worth it. All right, now I want to get to the most important topic in MPI performance. Oh, so by the way, this was your first MPI programming for most of you. How many of you wrote a program that deadlocked by mistake? Yeah, I mean, like it happens to everybody. So I used to think that, to debug codes in the old days, you wrote the code and it wouldn't compile, but then it would compile and it wouldn't run. Then it would run and give the wrong answer, and then finally, after a lot of work, you'd get it. But MPI induced new stages. It runs and it deadlocks before it runs and gets the wrong answer. And then it runs and it gets the right answer, but it's incredibly slow. In fact, it's super linear slowdown, not super linear speed up. So there's the additional work. All right. So what's the time? Message passing costs time, right? I send a message. Sometime later, the receiving process gets the data. By the way, sometime later, I get the processor back as well. So both me, the sender, and the receiver are waiting for this message. And if the message has n bytes, this one's dead. So n bytes. A reasonable notion is that the time to send that n-byte message is something like alpha plus beta n. It's, you fit it. This is a model that sort of tries to fit the data. Is it a good fit on a given machine? It's usually a crappy fit, but it behaves in the right general way. That is, very short messages where n is very small, like 0, for example, are dominated by that fixed cost alpha. Very long messages where n is millions, the alpha is insignificant, the beta n term dominates, and there's an intermediate value. So if you look at the achieved bandwidth as a function of the message size, bytes per second, delivered, you get something like that. Here n is so big that the only thing you see is beta, and here it's the alpha. And why you have that behavior, that's not in the model. The model wouldn't do that. All right. Oh no, maybe it is. Right? This is alpha. Here's my problem, that the halfway point is when alpha equals beta n. And you can get beta by seeing the asymptote. Beta is 1 over the asymptotic bandwidth. So it's easy to get beta by reading the curve that you get by experiment. And there are two ways to read alpha: by figuring out what it is from the asymptotic, from the middle, where you hit the middle bandwidth, because you say that's where alpha equals beta times this n. or it should be the intercept. And they typically give two different numbers because reality is more complicated than my simple model. But this is still a very useful thing to do. And if you do that on a modern machine, and let's say use the midpoint measurement for alpha, then a typical number would be, I thought I might run out of gas. It might typically be the case that alpha is around 2,000 beta. A 2,000 byte message is half the peak bandwidth, is what that says. Short messages are expensive, long messages are better, even though they take longer. So one obvious thing is if I have several things to send to somebody else, combine them in one message. Pay the alpha once. There's a whole raft of papers being written these days called communication avoiding algorithms. The first thing they do is try and reduce the total number of messages, total number of bytes sent to deal with the beta n term, but then they also try and reduce the number of messages sent to reduce the alpha n term. Have you seen the basic idea about implementing MPI all gather or MPI all reduce? Let's talk about MPI all reduce. To implement MPI all reduce, remember, let's do an 8 processor all reduce. Each of these 8 processors starts with a vector, different on every processor, same length. And let's say we're using a summation. So when we're done, every processor will have a copy of the sum of all those vectors. All right, the reduce means add the vectors together. The all means they all get a copy. It's replicated. So one way to do that is these two exchange their vectors and add them together. And now they have the sum of those two vectors. Both of them have it. Same here, same here, same here. Then 0 and 2 exchange, 1 and 3 exchange, 4 and 6, 5 and 7. Now, all 4 of these processors have the sum of their original vectors. And with one more step, of course, 0 is going to exchange with 4, etc. Done. That's the butterfly reduce, it's called. You can do that scheme for anything like a barrier, meaning everybody stop here until all have arrived, which is just an all reduce with the OR operation. So log base 2 of number of processors, that's the number of stages, and at each stage it would be alpha plus beta n, where n is the length of the vector. So that would be alpha plus beta n log 2 of p, number of processors. Turns out there's a very clever way to do this that takes away the log p dependence from the beta n term. And you can get it down to alpha log p plus beta n, or maybe the beta prime n. That's a good reason to use the library and not write it yourself this way. All right, so this communication cost model, enables us to figure out optimizations like that. So I want to just kind of, I got 5 minutes or something like that? 10 after 3, 4, 10 after 4.
Yeah, the class technically goes to 4:30.
Oh, 4:30. Ooh, good. We got a lot of time. But slow me down if you'd like, or leave, or whatever. So I'm going to use that model and that way of thinking. And knowing that model about the basic cost of a message, let's improve our model of the machine, the sort of fundamental MPI model of the machine, which is that there's this amorphous network that sends messages, and every processor has its own private memory. And they connect to the network to send messages. That's the generic cluster machine model that underlies MPI. In other words, the only memory I can see is the memory that only I can see. And what we're doing is we're just saying this connection has a bandwidth, which is expressed by that number beta. Beta seconds per byte. Normally it's the other way around, 1 over beta bytes per second. Now, consider all reduce. Everybody has n to begin with. And at the end, everybody's got n. And surely all of my values have to somehow make it out into the network. Otherwise, how's anybody else going to find out what they were? And surely all of the final result has to come into me from the network. So I know that each of them has to communicate at least n data, or 2n bytes, n in each direction, minimum, maybe more. In my naive butterfly method, they communicated log p times n. But just thinking about the problem, n was the minimum possible. And indeed, there's a clever way to do it that achieves that bound. So a lower bound on the communication time for any MPI computation goes by saying, of all processors, which processor must communicate the most data? Then beta times that number of bytes is a lower bound on the amount of runtime. All right. So you probably have heard about Mapreduce. Have you heard about Mapreduce? Mapreduce is something Google has invented as a sort of generic way of programming. It's the business computing MPI. But in Mapreduce, you never write a sender or receive. You can only write one kind of program. Every processor reads a disk file and generates a whole lot of pairs called a key and a value, and then gives all of those key value pairs to the Mapreduce framework. The Mapreduce framework then sends the key value pairs to reducers. It does a gigantic all-to-all in such a way that all of the key value pairs with a given key wind up on one of the reducers, and then that reducer does something to them. So you have the mappers that create the key value pairs and the reducers that combine the key value pairs. And their canonical example is word count. If I have a lot of disk files, I give each mapper its own disk file. It does a word count, so the key is the word and the value is the number of occurrences of that word. And then you throw those into the Mapreduce framework. It sorts according to the words and gives each reducer some of the words and all of the counts from the mappers for that word, and it just adds those counts together. And you're done. Well, Mapreduce is cute because you don't have to write send and receive. All it is an all-to-all. It's like one MPI call. But the point is there's an enormous communication and no locality exploited. Every key value pair has to be communicated across the network. And in fact, when they try and parallelize Mapreduce codes and scale up the number of processors, they see a typical thing like this. Speed up. Oh, in the beginning of parallel matrix computation, when they tried to parallelize sparse matrix factorization, they saw a curve like this. Same thing. So we're going to analyze that now a little further. I'm going to do something real simple. Speaking about Google, Larry Page's PageRank algorithm, which is to compute, it computes, all right. It repeatedly does this. It takes some big matrix, call it A, and a vector, call it X. It computes the product of A times X, a vector Y. But then it has to bring Y back and goes around and uses Y as the next X. It's the power method. If you've taken numerical linear algebra, this is a way of computing the eigenvector of A that corresponds to the largest eigenvalue of A. And you do that, and you can rank websites and do a lot of other cool things, because one use of this is to compute the steady state distribution of random walkers in a graph, or the steady state of a Markov process. So we want to repeatedly take a matrix A, multiply it by a vector X, get the result, but then bring it back, because we're going to do the same thing again and again and again using the result Y as the next X. Coming back to the first thing I asked, it's all about how you distribute the data. So suggest to me a distribution of the data. It should allow parallel computing, and it should be load balanced for sure. There are obvious things here. Obvious number one. Let's do a row-wise split. That's the most obvious, probably. Now, that's of A. So this is rank 0, 1, 2, 3 on a 4-rank machine. Quarter of the rows, et cetera, et cetera. Now, how about X? Where do I want X? Considering replicate X. Got to replicate X. Why? Because 0 needs to multiply his n over 4 by n thing by all of X, which is a vector of size n. So does 1, so does 2. So you replicate X. So X is everywhere. So he does his thing, and he computes this little chunk of Y, and this guy computes the next chunk of Y, and the next chunk of Y, and the next chunk of Y. Now I've got Y, but Y is distributed, not replicated. I need to call MPI underscore all gather. Gather would gather them together on rank 6. To replicate, you would call all gather. Yes. So you have one call to MPI all gather. It's pretty simple to write this code. It's like the world's easiest MPI program. It has no sequential fraction. It's perfectly load balanced for the point of view of memory and work, and it sucks. Why? Well, the all gather is bringing in all of X into every processor. That processor has a fixed size bandwidth into the network. So if I fix n, the size of the matrix, and I increase p, what happens to the communication time or to that communication lower bound? No matter what p is, I'm always bringing the whole of X in to me every iteration. So here's the speed up curve. That's negligible, then that becomes equal to the computation time, and now that communication time, which is not decreasing as I increase p, is the dominant term. So you hit a wall. Okay. Well, I'll fix that. Let's divide this thing up by columns. Rank 0, 1, 2, 3. How will I divide X in this case? You're thinking right. Yeah. So you'll block X now. X is going to be the first chunk here, the second chunk here, the second chunk here, the second chunk. So X is going to be distributed in a way corresponding to the distribution of the columns of A. And now everybody has the right piece of X to start with. So they locally compute my piece of A times my chunk of X, and they get a vector of length n, and he, all different, which, if they were added together, would give me y.
Why?
Oh, well, that's the definition of matrix times vector. All right, the ith element of y sub I, is the sum of the inner product of the ith row of A, which is spread across these 4 processors, and the vector x. So this guy has computed some terms from that inner product, and this guy has computed some and some and some, and they should all be added together, but he can only add together the pieces he has. So these 4 subsums now have to be combined to produce y sub I. Good question. Okay, so MPI reduce would do it, but it would leave y on one processor. MPI all reduce would do it, then everybody would have all of y, even though they only need a chunk of y. Well, all of y includes the chunk I need. And there's a flavor, there's a funny MPI collective called MPI reduce scatter, which is exactly what you want here, and takes these vectors, one on each, adds them together, and leaves the result scattered just as you like. Is that going to fix our problem? Think about the communication required. Think about the outgoing communication. He's got this vector. He contributes it to reduce scatter. Only a small fraction of it, 1/5, is actually relevant to the result that he's getting. The others must leave. So clearly, again, O of n data are going to leave every processor. And the communication time does not reduce as you increase the number of processors. Who's got a guess as to the, if distribution by rows didn't work and distribution by columns didn't work, what are we going to do?
Breaking up into blocks.
Yeah. Where did the blocks idea come from? Tell me why you think that's.
Because then you're always only going to need a portion of X and always only going to affect a portion of Y.
Yeah, exactly. You may have seen things like this many times in computational complexity, where you find that one extreme is no good and the other extreme is no good, and if you pick the point in the middle, you reduce something to the square root of what it used to be. So if I have 16 processors, suppose, rather than 16 panels this way or 16 block rows this way, I think of the matrix as being a 4x4 matrix of blocks. In general, the block dimension here is going to be n over the square root of the number of processors. Right? Take p processors, think of it as a square root of p by square root of p mesh. Hopefully p is well behaved. Don't ever ask for 17 processors. If you had 8, you'd make it 2x4, so it doesn't have to be perfect. But you want it to be as square as you can do it. All right? Now what happens? Well, you start with this piece of X replicated on all 4 of those. The 0th piece of X replicated on all 4 of those. That's the starting condition. And so on. Everybody computes a vector by multiplying the local A by the local X. Then within the first row, you do a reduced scatter of those guys. And now you've got the first piece of Y Oh no, I think you do an all reduce. So you now have the first piece of y replicated here, the second piece of y replicated here, the third piece replicated here, the fourth piece replicated here. Then you need to do an exchange of information because the first piece of y for the next iteration needs to be known here because it's now the first piece of x, and you computed it replicated here. So what happens is these exchange information, these exchange, these exchange, these exchange. The point is all of the communication is in chunks of size n over root p, which is certainly an improvement over n. So I think you discover, if you pursue the analysis, that if you scale up the problem n with p so that n squared is on the order of p. This is called weak scaling, where you increase the problem with the number of processors. And there's a reason why I want n squared to be order p here. It gets back to your answer to my first question. The amount of memory in the problem here is n squared. If you do that, and you use either of the 1D distributions, you get efficiency that drops to 0 as both the problem and the p increase. But if you use the 2D distribution, you get efficiency that's constant. You can grow the machine and the problem arbitrarily large, and you'll have a, depending on the constant here, you'll have a fixed bounded efficiency, might be 0.1, might be 0.2, but at least it stays away from 0. It doesn't drop to 0 as you scale the problem in the machine. You could work out the details of that. So that's the main issue in MPI performance. There are all these other things, but the main issue is understanding communication cost, the dominant effect of message volume on communication cost, the beta n term, and using a back-of-the-envelope kind of approach. I mean, the scoundrel's approach is just write a crappy algorithm and then spend months and months using performance analysis tools to discover that it's communicating too much. Whereas think first, distribute the matrix later is the much better way to go. Is a back-of-the-envelope calculation based on the amount of traffic in and out of each node is going to help you tremendously to get a handle on reducing the communication. Good. All right. Nice to meet you guys.